Okay, so we promised that we will generate the examples of non-abelian groups in the next section. So let's start talking about a family of groups called permutation groups. Permutation groups. So first of all, what is a permutation? Permutation. So a permutation is a bijection defined on a set X. So I denote the bijection as pi that maps X to itself. So here is an example. Let's say X has six symbols G, R, O, U, P, and S. So these are the elements of X. Then I can think about a permutation. For example, if it applies on G, it gives me R. If it applies on R, it gives me U. If I apply it on O, it gives me P. If I apply it on U, it gives me G. When applied on P, it gives me O, and it gives an idea. So if I apply it on S, it gives me S. So this is a bijection, and therefore this is a perfect example of a permutation. Good. Now, the first question, it actually appears quite a bit of times in the entire abstract algebra course. So, what is the best way to represent it? Now, this way of representing it is pretty cumbersome. So, we have to write too many things. Well, one thing that comes to mind is any bijection is applied on each of the elements of the set and it produces the output. So, what I can do rather, I can omit unnecessary things from here and I can just write the input arguments on the first row G, R, O, U, P, S, and on the second row exactly corresponding to the each element written on the first row I can write where that permutation or bijection takes me. So G goes to R, R goes to U, O goes to P, U goes to G, P to O, and S is S. And this is one way I can represent a permutation. But even this is quite a bit. For example, if a set X has n number of symbols, then in order to represent one permutation, you need to write 2n number of symbols. So the question is there a better way? Is there a better way to represent permutations? Well, it turns out that there is one, and let us denote that method. We call it the cycle notation. The cycle notation. So again, so if we take the same example that we just showed, um, in cycle notation, what we are going to do, we are going to write in the following way. So first check under the repeated application of the permutation where these alphabets are going. So for example, G goes to R. And where is R going? R goes to U. Now, if you apply the permutation on U, it gives you back G. So U goes to G, right? Okay. Now, what about what is left? O, P, and S. So where does O go? So if you apply it on O, O actually goes to P, and P goes back to O. And S is the only element that goes back to itself. Well, now these picture exhaustively and sufficiently can represent a specific permutation. And simplifying it little bit, we can write it like this: G comma R comma U. This is a tuple, and then O comma P and S. Now this is a perfectly I would say, a complete way to represent a single permutation, and this is adopted quite heavily in the math community. So each of these tuples are called cycles, and the length of a cycle is denoted in order to specify that particular cycle. So we have one 3 cycle, one 2 cycle, and one cycle. It is often customary that you don't have to specify one cycle because it doesn't make any difference. So this is same as G comma R comma U and then O comma P. Okay, so this cycle notation is sufficient, as we discussed, to represent a single permutation. And also note that these cycles are disjoint cycles. So, okay, so these cycles are disjoint cycles, and this entire algorithm that I showed here that can convert a cumbersome representation of permutation to the cycle notation will also tell you two things. So, the first one is any permutation can be represented as disjoint cycles the way exactly I have written it here. And these disjoint cycles are also unique, and that you can convince yourself, and they are often called cycle decomposition. And as we just discussed, that cycle decomposition is unique. You can convince yourself because since there is no common element on the first cycle and on the second cycle. It doesn't matter how you come at this point. um, they will you always come to this particular point, so the decomposition will denote the same bijection. And also another thing to note here, since there is no common element, it doesn't matter which cycle you write first. So this is same as O comma P and then G comma R comma U. You can start from whichever alphabet you want, and you will arrive at either of these two way of representing this particular bijection or permutation. So the final thing before we conclude this section is, as you know, that set of all bijections for a given set, they actually form a group. And that is, I would say, quite intuitive because bijection means they have inverse. Identity map is also a bijection, so that is actually the identity. Bijections are associative, and of course, bijections are closed. any bijection will give you another arrangement of that particular set, right? The set of all bijections under composition, therefore form a group. So that's the third thing that we are learning here, that set of all bijections form a group. It turns out that this group is extremely important in the study of group theory and known as symmetric symmetric group symmetric group. And also, you can convince yourself easily that if a set has n number of elements, then of course there is n factorial way you can permute them. So, symmetric group, the order of the symmetric group is n factorial. Now, the interesting question is, what are possible subgroups of the symmetric group? That's what we're going to discuss in the next section. Okay, so before we investigate the subgroups of a symmetric group, let's first show through an example that symmetric group actually is non-abelian in general. And when I say in general, it means that of course S1 and S2, they have to be abelian with 1 and 2 elements, but S3 in greater than equal to 3, this is actually non-abelian. So through an example, let's show that S3 is non-abelian. Good. Now, let's say that our S, the set in this discussion, consists of three symbols. I can name them however I want. Let's just, without any loss of generality, let's just call them 1, 2, and 3. And let's take two permutations. So let's say A is my first permutation, and in the descriptive notation, um, let's say the permutation is 3, 1, 2. So it actually takes 1 to 1 to 3, 2 to 1, and 3 to 2. And let's say B is another permutation that takes 1 to 3 to 3 to 1. Okay, so we will show that we will show through this example that A times B is not equal to B times A. Okay, good. So also this is good. This is a good exercise because um, we will see through this exercise that how to deal with cycle notations. Let's convert everything into cycle notation. So if I try to convert the permutations A and B in the cycle notation, A will look like this. It has a single cycle, 1, 3, 2, because it actually maps 1 to 3, 3 to 2, and 2 back to 1, as you can see in the descriptive notation. And similarly, B will look like B maps 1 to 3 and 3 to 1, and 2 remains unchanged, and we don't write one cycle, so B will look like this. Now here is a very crucial thing. This is a representation of cycle decomposition where each cycle is disjoint, so you won't find any common element between two cycles. But as we say that permutations form a group, so you should be able to multiply two different permutations. And when you multiply, there is no guarantee that it will remain a disjoint cycle as well, right? So for example, if I try to find out A times B in cycle notation, it will look like 1, 3, 2, and then times 1, 3. Now notice that it is not a cycle decomposition because they are not disjoint cycles. 1 and 3, they are common on both cycles. So the question is, how are we going to represent this in cycle decomposition? How are we going to find the disjoint cycles? Well, the way to do that for this is our rudimentary law, essentially just to check one by one where the elements are going. So let's see where one is going. So what you're going to do, you first, let's say, apply this entire thing to one, and after it goes through your first cycle, it will give you three. And when it goes through your second one, from, of course, everything has to happen from right to left, because that's how you are applying it. You are acting on each of the elements on the set. So and then 3 goes to 2, right? So what I find here is 1 goes to 2. How about 2? Now, similarly, using the similar logic, notice that 2 remains unchanged after the second cycle, and the first one, 2 goes back to 1. So this is a cycle. And what about 3? Well, 3, same logic. The second cycle will map 3 to 1, but then 1 gets mapped to 3 again by the first one, so 3 remains unchanged. So this is going to be the cycle decomposition for A times B. So it has a single cycle. Okay, now using the same method, you can try to find out B times A. Um, and of course, B times A, if you write it in the multiplicative form, it will look like 1 comma 3 times 1 comma 3 comma 2. Now you can check using exactly the same technique. You can check one by one where the elements are going by applying these entire cycle um, multiplication on each element. You should be able to see that the disjoint cycle, the cycle decomposition of B times A, will look like this: 2 comma 3. Now, of course, as you can see, 1 comma 2, this cycle is not equal to 2 comma 3, will automatically imply what we were looking for, which is A times B is not equal to B times A. So in general, this is a non-abelian group. Okay, so this is true for S3, but this is true for all n greater than 3. We'll get there at some point, but it is crucial also for you to quickly read through the cycle when they're multiplied and where they're not disjoint, and then represent it in the cycle decomposition, and then understand the how it is acting on each and every element of the set. Okay, in order to appreciate the subgroups of a symmetric group better, let me introduce some additional definitions here. So the first thing that we will see is called parity of a permutation. So we can say that a permutation pi is even, or it has an even parity, if it has even number of even cycles. And even cycles means cycles of even length. So the length of a cycle is an even number. This is where the permutation is even, and otherwise we call odd. We call the permutation to be odd, or it has an odd parity. Good. Now, a very important thing next is a specific permutation called transposition. So, a transposition is actually transposition is just a two cycle. So it's a cycle whose length is 2. Okay. So the crucial thing here, and this is can be your optional homework, that any arbitrary cycle, so for example a1, a2 up to ak, which is an any arbitrary cycle, and of course this is also a cycle decomposition because I just have one cycle, but it can be written as a product of transpositions using this formula. The formula is the following: a1 ak, a1 ak minus 1, and all the way to a1 comma a3 and a1 comma a2. So this is the formula. I mean, this can be your optional homework again, and you can convince yourself first by checking with um, some k and then probably proving it through induction. But you can see that any arbitrary k cycle can be written as a product of transpositions. Now note that this is actually not unique, and when I say this is not unique, you can actually write, for example, let's take an example. So let's say I have 1, 2, 3, 4, 5. This is my cycle. I can write it in the product of transpositions like this: 1 comma 5, 1 comma 4, 1 comma 3, 1 comma 2. But I can also write it as 1 comma 4, 1 comma 5, 1 comma 4 again, 1 comma 3, 1 comma 2, and 3 comma 5. So check this if this expression is correct, but this is something you should get. So this is of course not unique. Cycle decomposition is unique, but decomposing an arbitrary cycle into the product of transpositions is not necessarily unique. Okay, now next what we're going to do, we will show that transposition plays an important role in the parity. Okay, so what we have just seen is that a permutation can also be decomposed into transpositions, right? So earlier we said the permutation can be decomposed into disjoint cycles called cycle decomposition. And to determine if a permutation is even or odd from its cycle decomposition is just to count the even number of, if it has even number of even cycles or not. If it has even number of even cycles, then it is even, otherwise it is odd. Now there exists a similar criteria that is pretty straightforward. What we, from the exercise that we had done, that a permutation pi is even if it has even number of transpositions and odd otherwise. Okay, good. So that means that even if I can write a permutation, decomposing it into transpositions, just by counting the number of transpositions, I can determine if the permutation is odd or even. And uh, it also means that if I have a permutation which is even, and if I multiply that with with some transposition, let's say a and b, then the parity changes, so it becomes odd. The parity flips. Okay, now all these things can be summarized by defining a function called sine function for a permutation that maps any permutation to its parity. So the sine function essentially says that any sine of any permutation pi is plus 1 if pi is even, and it equals to minus 1 if pi is odd. Okay, let's now look at the subgroups of the symmetric group Sn. So one thing to clarify, that the parity is actually a property of a permutation itself, which is why property of permutation, which is why even though decomposition of a permutation into transpositions, it's not unique, but even if you, and this is the exercise that we had done, even if you decompose it in two different ways, you can count the number of cycles, and that will show its parity, and that will remain unchanged. You will, if the permutation is of even parity, you will always find even number of transpositions in that decomposition, even though the decomposition into transposition is not unique. Okay, and we summarized it with the sine function, but there is a very important property of this sine function. So if pi 1 and pi 2 are two different permutations, then pi 1 times pi 2, because they form a group, pi 1 times pi 2 is another permutation. And if I apply the sine function on pi 1 times pi 2, this is actually multiplicative. So what I get is sine of pi 1 times sine of pi 2. Good. Now these things actually um, indicate um, quite clearly that even permutations form a subgroup of Sn, right? And this subgroup is denoted as An. But since there are exactly as many even permutation and as many odd permutation or odd permutations in Sn, um, it also implies that the order of this subgroup An is order of the subgroup Sn divided by 2, which means n factorial divided by 2. So this group is called the alternating group. Alternating group. So let me digress a little bit and let me tell you an interesting story that is relevant for an alternating group. So there is something called 15 puzzle. I don't know if you have seen that. I saw that when I was in my childhood. So the puzzle looks like this. So you have a square, and you have 4 rows and 4 columns, and all these squares has a number written here: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and then 15, 14. And this last square, it's actually blank. So the idea is that you slide these squares, like you can put 12 here and then 12 this position at 12 it goes blank, and then you can push 8 or 11 here and you slide it, and the ultimate goal is you need to swap this 15 and 14, right, so that it goes to the natural order like 13, 14, 15. So this actually became a craze in 1880. I think somebody called Sam Lloyd, as far as I can remember. So he actually launched this game and announced some prize along with it. And then people were trying to solve this problem all the time, although he was not a discoverer. And then it was realized that um, this puzzle was actually solved in mid 1870s or something by two mathematicians. I think their name is Johnson and Story. These two mathematicians, and what they managed to show using group theory around 1875, that when you perform the slides, um, when you perform the slides, and if you make sure that the position of this this blank square is exactly at the fixed location. So you can slide multiple squares in different ways, but then at the end of it, make sure that the position of this blank square at exactly at the bottom right corner. Then all these permutations can only be even permutations. It cannot be odd. And then from this, you can easily conclude that why it is impossible, and that's exactly what they concluded in their paper, that it is actually impossible to swap 14 and 15, because swapping this would require to flip your parity, and even permutations form a group, and you are inside that group, so you are restricted by the closure property of that group. So once that was realized, the craze went down. But it's a funny story that how symmetry plays an important role in what you can and cannot do in some simple games. But this is exactly relevant to this game, because for 15 puzzle, for a fixed position of the blank square, the all the moves that you can do, this actually belongs to the group A15. You can actually show that for 2k minus 1 puzzle, this is actually a 2k minus 1. This actually moves in the falls in the category of a 2k minus 1, this alternating group of even permutations. So good. So this is a fun application, but just know that the parity is a very important thing, and this is applied in physics and in many other fields where people are extensively using group theory, and use parity to understand various other symmetries of nature, and compute other quantities that are relevant in the physical universe. Okay, great. So coming back to our discussion again on the subgroups of the symmetric group, let's look at another subgroup of the symmetric group of SN called the dihedral group. So dihedral group is actually about the rotation and flips of a polygon. So let's say I have a hexagon that looks like this.
And I can name the vertices as 1, 2, 3, 4, 5, and 6. Now, as you can imagine, that any 60-degree rotation, either counterclockwise or clockwise, or any flip about some axis of symmetry, will permute these vertices, these vertices 1, 2, 3, 4, 5, 6. So let me denote them by the set X, where the member of the set X is the vertices 1, 2, 3, 4, 5, 5, and 6. So, and the claim is that any rotation or any flip will create a permutation on this set of X, right? Now, these rotations and flips, let's find a way to represent them. Let's say R represents uh, rotation rotation about the smallest possible angle, which is 60 degree for a hexagon, and F denotes a flip or a reflection about this axis. Then the dihedral group for an n-sided polygon is represented as D2n, and there is a reason why the subscript is 2n. The member of this group can be written as, of course, identity. That means I am not rotating, neither I am flipping. And then R, rotating with the smallest angle possible, which is um, that preserve the symmetry, which is 360-degree divided by n. And then R square, and all the way to R to the n minus 1. And R to the n is same as identity, because that means you rotate it all the way to 360-degree. But there are other elements because there is an F. So similarly, F and RF, which means flip followed by rotation, and then R square F, and all the way to R to the n minus 1 and F. Now, the criteria here is, of course, that R to the n is same as identity, and F square is same as identity, right? If you flip it twice, then it will give you the same vertices you started with. Now, notice that, of course, the number of elements in D2n is actually 2n. So the order of dihedral group D2n um, equals to 2n. So this is clearly a subgroup, because end of the day this is a permutation group, and any permutation group has to be a subgroup of the group of all permutations, which is the symmetric group. And this is a very important group that gets used in crystallography and other applications as well, um, and symbolically represented this way. So a very important example of a subgroup that people consider as one of the subgroups of Sn. Okay, so as our final example, we will discuss not specific subgroup of Sn, but a family of subgroups of Sn called the transitive subgroups of Sn. Now, these type of subgroups, they play a crucial role in Galois theory, and we will come back in details as we progress in our course. But here, what we will do, we'll just define them and probably see a few examples for some small n. Okay, so let's say that you have a set X of n symbols, 1 to up to n, and Sn is our symmetric group with all the permutations. Now, any subgroup G of Sn is called transitive if for any pair of elements, let's say x1, x2, in X, there exists a permutation pi in G such that pi of x1 equal to x2. So, in simple language, what it means is you can choose any two element from your set, and there will always a permutation that we'll find in the group that maps one of the elements to the other. Okay. So, and as I mentioned, that this is a very important and subgroup class of subgroups, and that play a very crucial role in Galois, and we will come back. Now, for n equals to 1 and 2, for n equals to 1 and 2, this is a trivial example. So, the entire Sn is the only transitive subgroup of Sn itself. For n equal to 3, you can show that other than S3, A3 is also a transitive subgroup of S3. S3. For n equals to 4, the list actually grows, and we are not going to go to that direction right now. But this will be our center stage at some point. Okay, great. So this actually concludes our discussion on permutation groups. And in the next section, we will um, use some of the insights that we had developed here, because this is the section that was dedicated to one of the first section where we talked about non-Abelian groups. And now we will go back to our discussion on groups and look into the details of the group structure and prove some important theorems. Okay, thank you.